In this lesson, we're going to use trigonometry and 3D coordinate geometry to answer questions about shapes.
Okay, so in this lesson here, what we're going to do here is a similar sort of coordinate geometry that we've done before in 3 dimensions. But we're going to look at problems here that are going to require some trigonometry for us to solve. Now, the way you got to do this is when you're looking at the picture here in 3 dimensions, to use trigonometry here, typically what we're going to do is we're going to find that plane, the plane that cuts this object in the way that we want, so that we can actually apply our 2-dimensional trigonometry, right? Because you're comfortable with trigonometry, your SOHCAHTOA, if you will, with your sine law and your cosine law and so on. We're comfortable with that in 2 dimensions. So when we get a 3-dimensional problem like this, and you've done these before in earlier math courses, but the only difference between what you did back then and what you're doing now is kind of how you have to get the information that you need. So in previous questions, you would have done 3-dimensional trigonometry, and what you would have done is you would have cut the 3-dimensional problem into planes that you can do your little bit of trig on, and then you move from one plane to the next here. Well, we're going to do a very, very similar thing here, except that in previous questions, we would have given you the lengths and the widths and the heights of all the objects that we're working with. Here, we're not. We're giving you the coordinates of the points that we're working with, and you've got to go just that one step further and figure out what those lengths are that you need. Now, sometimes this can get a little bit confusing, because what you have to do is you have to see that plane and see the pieces that you need before you jump in. Okay, well, you know what? Let's just use the example here that I was referring to just a couple seconds ago. So the question here says, in the following diagram, the angle between the line segment EC and the plane ABCO. Okay, so ABCO, and O is going to refer to the origin here, is going to be the bottom of this prism that you're seeing right now. Now, EC is that line segment that goes from this corner all the way down to that corner right there, C. Now, so it's going from this corner right here on one end of this box to the exact opposite end here. And the question that we're asking is, what angle does that make with the plane? Now, we got to be careful here, okay? Because there's all sorts of angles that you could make between this line and the plane. You could make all sorts of them. But what is it that I'm actually referring to? Like, do I want the angle between EC and EBC? Well, BC is in that plane. So if I found that this length right here, I could figure out the angle. Do they want the angle between this one and the line, let's say CO? Okay, because CO is in that plane. And when you could think about it, you could get kind of lost in this little problem here, but the most obvious thing that they want you to figure out here is the angle between this line and the line in the plane that's directly below it in the direction of the plane. So it would be like AC. So really what we're trying to figure out here is the angle between EC and AC. Okay? It's basically like this. If think about it like this, if you're standing in front of a wall and I ask you, how far is the wall away from you, right? Okay, like you've got your wall here, and here you are standing right here. Well, you don't go off at an angle and measure the distance like that. You go right to the wall. Okay, that is clearly what I'm asking you to do here. It's the same thing here. So you've got to make that decision. What plane that cuts this object? In what plane am I going to do the trigonometry that I'm interested in? And so it's going to be the one right here that cuts through and leaves EC and AC together in the same plane. So what I want is that angle right there. Now, is a whole long explanation for something that is probably very, very straightforward and obvious to a lot of you. Now, this next little section here is just doing exactly what I just did with you. Now that we've established what plane we're working in, we want to figure out how we're going to look at that angle or how we're going to get it. Well, what's nice about this is that when I connect these lines here, so EC and AC there, the line EA is perpendicular to that base. So I know that that angle right there is going to be 90 degrees, which means I'm using just basic trigonometry here. And so, well, I've got a few options open to me, quite honestly. I can do a few things here. What we might want to do, first of all, is figure out what the length of AE is, okay, which is going to be this side right here. Well, AE is 3 units. Okay. When I take a look at my point D here, and maybe zoom in just a little bit here. When I take a look at point D here, notice that in the Z direction, I'm 3 units up. Okay, so from the origin, 3 units up here. Well, it's a safe assumption that all of these points here, this D, G, F, and E, are all going to be the same height because this is a rectangular prism. So E here, directly above A, E here is going to have the coordinates. Well, it's going to have the same x coordinate as A because it's in the same distance in that direction. It hasn't been moved anywhere in the y direction, that's out this way, and it's 3 units up. Okay? So I can grab the coordinates of that point there fairly easily from my diagram. Now granted, I am making the assumption here that this is a rectangular prism and that the corners here are all 90-degree corners, but that's a really quite a safe assumption here. So now, if you're not comfortable just identifying that that is 3 units up, the difference between those points is 3 units, well, you can use your Pythagorean theorem, your 3-dimensional version of the Pythagorean theorem. Okay, so the difference of the x coordinates, oh, sorry, I didn't do that here. Sorry, I was assuming that I did. Let's do it over here. If you're not comfortable with that, you can get AE. That is going to be the difference of the x coordinates, which will be 5 minus 5 squared. The difference of the y coordinates, 0 minus 0. Yeah. Oh, I don't have it handy here. I'll have to go grab that in a second. So, sorry, ignore that little comma there. Don't know why I put it there. Squared, and then plus 3 minus 0 squared. All square rooted. And that's just going to be 0, 0, and then 9, and the square root of 9 is going to be 3. So if you're not comfortable just making that call, well, clearly our Pythagorean theorem there will give that to us. Now we can come up with the distance AC, and we have both coordinates there, okay, for A and C. And so that's going to be the difference between the x coordinates, so 0 minus 5 squared, plus the difference in the y coordinates, 4 minus 0 squared. And then they're both on the same plane vertically, so their z coordinates are the same. And when we put that together, we're going to get the square root of negative 5 squared plus 4 squared. So that's going to be 25 plus 16. Now we're looking at the square root of 41. That is the length AC. And so now, if you want the angle there, all we need is the tangent ratio, right? Because I've got the side opposite, and now I've got the side adjacent. And when I do that, set up my tangent ratio, 3 over the square root of 41, I get that the angle there is approximately 25.1 degrees, or what you might normally write there, okay, is approximately 25 degrees. Often we round these things to the nearest whole degree. Anyway, so that's kind of an example. So the trig is relatively straightforward. You've done that sort of 3-dimensional trig before. It's just that the side lengths that we need are hidden a little deeper. There is a layer of complexity that we put over this problem when we just give you the coordinates of the vertices, and not even all of the vertices, right? I never gave you the coordinate for E. You have to kind of intuit that out of the problem there. Okay, this next example we're going to look at here, it says if you're given the point A, negative 2, 0, 1, B is 1, 4, 5, and C is 0, negative 2, 6, then we're going to find the measure of angle ABC. So starting at A, the vertex of the angle is going to be at B, and then it's going to end at C. Okay, that's the final point, the end point of that line segment. So what we've got here, maybe I'll go down here and draw this. So we've got here point A, point A, point B, point C, and we're looking for this angle right here. Now, the first thing that we want to do is identify the plane that we're going to do the trigonometry in. But the beautiful thing about a problem like this is when you've got 2 points in 3-dimensional space, let's just ignore the C there. If you've got 2 points in 3-dimensional space, that defines a line, okay? All I need is one other point that's not collinear with those two. Like if I pick a point over here, if it's in the same straight line, well, that doesn't change anything. It's still, I've only defined a line here. But as soon as I define one other point there, that defines a plane. So when I give you those 3 points, and I give you just those 3 points, I have inadvertently defined a plane for you. So now all we need to do to figure this out, just think about this. Okay, if I know all of those points here, what can I do to get that angle? Well, based on the endpoints here, I don't know if this is going to be a right angle triangle. In fact, I think the odds are pretty good that it's not. So if I connect those, is there any way that I can figure out that angle? Well, yeah. Because I have the coordinates of all 3 points, I can figure out the length of AC, I can figure out the length of AB, and I can figure out the length of BC. Well, I don't need to just use my primary trig ratios. I can use the cosine law to figure this out here. And this is exactly what is like half an inch or so above what my work here. Okay, so I'm going to use the cosine law to figure that out. So now all I got to do is plug in my coordinates into my my three-dimensional Pythagorean theorem here. And actually, you'll notice a little bit of a notation thing. When I don't put the line segment over top, that implies that I'm referring to the length of the line that connects A and B. Just a little notation thing. If you put the little line segment on top, then you're referring specifically to that line segment. Take it away and you're referring to the length. At least that is the notation, the way the notation works where I work here. Okay? So anyway, you get the length, get the length. We plug that in to our cosine law, and it spits out, zoom in, roughly 60.7 degrees, or approximately 61 degrees. Okay, that's how you would do that. Great little problem. Okay, let's try a problem here where that hasn't been kind of done for us ahead of time here. And so we'll work through this question right here, and it's basically the same as a lot of the other ones here. In the following diagram, M is the midpoint of line segment AB. Okay, I want to find angle ADO. So from A, clear across to D here, down to the origin, and then angle BMD. Okay, well, if you've probably noticed that what we need to do here is figure out some coordinates here. Well, in this particular problem, you aren't given the coordinates. What you're given is kind of where along the axes these little points are. So I have to intuit what the points are. So let's just talk about those. A has come along the x-axis here 3 units. Now I'm assuming out here is going to be positive, so 3, comma, and then it hasn't moved along the y-axis, hasn't moved along the z-axis, so it's going to be 0, 0. Okay, B over here, B has also come out the same number of units away from along the x-axis, so that's going to be 3. But this has also moved along the y-axis, and I can see from there it's going to be 6. But it's still at the 0 mark for the z-axis, so it's going to be 0 there. Turns out I don't need, well, I probably will need C actually at one point here, so let's figure out what C is. C is going to be the point, it is along the actual y-axis, so it's going to be 0 in the x direction, but it is 6 in the y direction, and it is still at 0 in the z direction, so we'll put 0 right there. And then I'm for sure going to need D. D has not moved anywhere in the x direction. Okay, you can see it's right above the C, so it's the same distance along in the y direction. But now it's been moved up, and it's 2 units up. Okay, there's that 2 right there along the z-axis, and D is in that top plane there. So those are the coordinates there. Now, and the origin, okay, clearly the origin is going to be 0, 0, 0. Hey, whoops, can't see that. No big deal. So now let's figure out that first one. I want to figure out the angle ADO. Well, if I connect them, and actually maybe what I'll do here is I'll use a pencil. I don't like using a pencil normally because it's not dark enough. Okay, I prefer using pencil to do my math here, but it's usually not dark enough here. But if I connect the origin to A, and then I connect the origin to D, okay, the D here is in the ZY plane. A has been moved out just along the x-axis here. The angle between these 2 line segments is going to be 90 degrees. And then if I connect A to D, and I wish you could kind of look down on it from this direction right here, because what you would see is a right angle triangle. Okay? The hypotenuse is going to be AD. And we got the base here, AO, And then this other line here, the leg of the triangle there is going to be OD. So what I really got to do here is figure out what the lengths of those guys are right there. Well, the length, okay, the distance, let's say, along AO. Well, I could plug in all of the coordinates there and figure this out here, but I already know that distance there is just 3. Okay, it only moved along the x-axis and then it came out to the point 3 here. So I already know that the distance AO there is going to be 3. Now what I need is the distance from O to D. This one is going to be a little bit more complicated. So the distance along OD. Now notice my notation here. I could have done OD capitalized without any line over top. I just like this notation a little bit better here. So that's going to be, well, my coordinates of D. I need the coordinates of D. So 0, 6, 2. And the origin is 0, 0, 0. So I'm going to compare the coordinates there. So this will be 0 minus 0 squared plus, oops, can you see that? Yeah. 6 minus 0 squared plus 2 minus 0 squared. Wow, okay, 0 minus 0 squared is 0. That's not doing anything. 6 minus 0 is going to be 6. Squared is 36. 2 minus 0 is going to be 2. Squared is 4. 36 and 4 is going to be 40. Okay, now I can simplify that. I mean, clearly I can. I could make that 2 root 10. Okay, and I probably should. That's actually not going to have much of an impact on the final answer here. So now what I've got is I've got the distance here along the one leg of the triangle. Okay, this is 3. And then I've got the other leg right there as 2 root 10. And what I wanted to do, basically, remember, I want to figure out what the angle is at D. It's got to be ADO. Okay, D, and based on the way I've drawn this here, here's my D, this is my A, here's my origin right there. I want this angle right here. So the tangent, okay, of angle D, or let's say, actually I should use the same notation here. Okay, the tangent of angle ADO is going to equal the opposite 3 over 2 root 10. And so now angle ADO will be the inverse tangent of 3 over 2 root 10. So now I'm just going to go to my calculator here. Okay, so it will be the inverse tangent of 3 divided by, now I need to make sure I put brackets here. More often than not, when people have troubles with this and they're getting weird results, it's because they're not putting the parentheses in the right location there, right? So I need to divide by that entire 2 root 10 there. And I get 25.4 degrees. 25 degrees is probably good enough. 25 degrees. Good. Now, the next part of this problem is to find the angle BMD. Okay, BMD. Now, in this case, just kind of erase, although it really didn't do anything to it, I'm just going to erase that. BMD, when I connect all those, BM is just going to be this right here. Now, that line segment there, like that AB, or in this case the MB, is going to be perpendicular to this face. So when I draw that line segment connecting D and B, it is going to be perpendicular to that line. Now, granted, the plane that it's in is at a bit of an angle, right? It's cutting through the middle of this thing. But it is still perpendicular to, if I choose the right plane here. Now, if I connect M to D, okay, there we go. Well, what I want are the coordinates of M. Well, first of all, let's figure this out here. So M is the midpoint of A and B. Okay, it's the midpoint of A and B. So it's going to be, okay, 3 plus 3 squared divided, wow, I can't believe I said that. 3 plus 3 divided by 2. Then it'll be 0 plus 6 divided by 2. And then it'll be 0 plus 0 divided by 2. Whoops, you can't see that. And so that's going to be 3, 3, 0. And those are the coordinates of M. Awesome. Now, if I want the angle BMD, I want that angle right there. I really just need 2 of the sides of that right angle triangle. It doesn't really even matter which ones. Let's find MB. Okay, so the distance along MB. Now, a number of you are already going to know that answer without me doing this. However, I feel somewhat obliged to go through and do this. So this is going to be, I'm going to use my Pythagorean theorem, so it's going to be 3 minus 3 squared plus 6 minus 3 squared plus 0 minus 0 squared, and I'm going to square root that. Okay, whoops. Now the 0 minus 0 squared is going to be nothing. It's going to go away. 3 minus 3 squared, well, that's 0 as well. 6 minus 3 is 3. Squared is 9, and the square root of 9 is 3. Now, for a whole bunch of you, if you really trust yourself on this one, you probably already saw, because of that 6 right here, that this line segment has to be 6 long, which means this also has to be 3, it has to be half of that. And yeah, that would have worked as well. Now, the other thing I want to find here is I could either find MD or I could find DB. I am more partial to finding the length along DB if for no other reason than I calculated M right now. I mean, I'm fairly confident in that. But because I calculated it, maybe I shouldn't be using that to make another calculation. Any little error that I make gets larger and larger if I start to use it in more and more calculations. So let's just find the length of BD here. So the length of DB, okay, and when I compare those two, here they are. So it will be 3 minus 0 squared plus 6 minus 6 squared plus 0 minus 2 squared. Okay, well, 3 minus 0 is 3 squared is 9. 6 minus 6 is 0. That term's going to go away. 0 minus 2 is negative 2 squared is 4. 9 and 4 is 13. Yeah, and that's as pretty as that's going to get. So now for me to figure out what the angle is here, I'm going to use tangent because I have the adjacent side and now the opposite. So the tangent of angle BMD is going to be the length of the opposite side here, this root 13, divided by the length of the adjacent side. So angle BMD is the inverse tangent of root 13 over 3. And pull out my calculator. Let's clear off what we just did. So the inverse tangent of the root of 13, and you want to make sure that you don't just hit divide by 3 right now. I need to get out of that. I need to use my arrow key to get out from underneath the radical. Divide by 3, that's what that should look like. And I get 50 degrees. So this is approximately equal to 50 degrees.